good week? Glad to see some of you made it back. We'll have a quiz on Wednesday. Let's get started. Lab this week we're doing the Wittig reaction. I think that's where we're pretty much at right now. We introduced that on Friday. Wittig reaction in the white handout. Wittig converts a carbonyl aldehyde or ketone to an alkene using a Wittig reagent. Wittig reagent is a ylid. Looks like this, 1,2-dicharged compound. Two key resonance structures for your ylid. This one here, good for mechanism. This one here, basically this double bonds to the carbon of the carbonyl and you have your alkene. We did the mechanism last time. Involved a four-membered ring and then it collapsed to give you two products plus triphenylphosphine oxide. The lab this week is a Wittig reaction. Instead of using a solvent, it's going to be done without solvent, grinding the reagents together in a mortar and pestle. Idea of a green reaction, more environmentally friendly. It will be a team effort. Each team should put their team name on the board and choose an aldehyde that you're going to be using. Write that beside your name, team name, first come, first serve, choice of aldehydes. Any questions about the mechanism for the Wittig reaction? The first, well, in this mechanism we did not have to deprotonate this here. This is a Wittig reagent, net neutral, it's already deprotonated. But sometimes you have to use a base to deprotonate. It depends on where you, at what point do you use the reagent. Okay, how do you make phosphorus ylids or Wittig reagents? Start with an alkyl halide. React these with triphenylphosphine. That's a solid. Phosphorus is a good nucleophile, and so, bam, SN2. Phosphorus now bonded. Kick off the Br minus. Phosphorus cannot go neutral though because it has no H to lose. You're just going to make this salt ion paired by an SN2 substitution. Now if you take this and treat it with a base, it can be a variety of bases, indolithium, KOH, sodium phosphate, etc. We can deprotonate here. We've got two H's here. Maybe we use hydroxide. Take an H, leave electrons behind. What do we get? We get this. Of course, you also get what else? If you want to balance that with KOH, you get water plus what? Plus KBr if you're using KOH. So, small molecule byproducts. Here's your ylid. Deprotonate. Why can we deprotonate this? Well, because it's slightly acidic. Well, why is it slightly acidic? Because the resulting anion is stabilized. Why is it stabilized? Stabilized by the phosphorus being electron pore pooling, but we can also do what here? Just like we did above. This is your product. That's your ylid. You can do resonance just like we do above. It's a resonance stabilized carbanion. Okay? Now in practice, sometimes you buy these and use them. But you actually just buy these salts here and use them. But if you're going to use this, you've got to include a base. So it will first do this. And indeed, the reaction you're doing this week, we use a base potassium phosphate. You can call this the Wittig reagent also, although it's really not the Wittig reagent until you deprotonate it. They're both pretty much called Wittig reagents. You got to deprotonate it. Once you deprotonate it, then this becomes your nucleophile that attacks carbonyl. Electrons up, oxygen attacks phosphorus, four-member ring, it collapses, you get alkene. Why triphenylphosphine? Why not trimethylphosphine? Well, if this was a methyl and there was a CH3 here, and there were three CH3s, you could deprotonate on either side. You make carbanion here or here by removing H. By those being all phenyls, there's no acidic H on your phenyl, and so it doesn't deprotonate over there. So triphenylphosphine. So all together now, you can take this, allyl ketone KOH, get your alkene. First step is what? Base deprotonating, do that, and then that reacts with aldehyde. Bam. Questions about making the Wittig reagents? All the way back to a simple SN2, triphenylphosphine. So, simple, show the product. Show the product of this Wittig reaction. They're already showing you a Wittig reagent here. That's really a minus and a plus if you want, right? Instead of double bonded to O, it's now double bonded to what? That carbon. And that carbon has what on it? A phenyl. There you go. Start to put them together, that resonance structure, boom. Basically, that half joins with that half. But you should not trust me. You should go back and look at the mechanism and see that that half joins with that half. How it does it. Now, this could be E or Z, right? The phenyl could be on the same side as the ethyl or the opposite. Which do you get? Which do you get? I'm sure it says it somewhere in the notes, doesn't it? Both? You get both? How do you know that? Because on the notes it says Wittig reaction is regioselective but generally not stereoselective. It gives easy isomers. Yeah. On the yellow sheet there. So we get that plus what? Do we get the alkene here? No. The Wittig gives a precise alkene, a precise regioisomer. If you remember, when you do E1 or E2, you often have to consider which alkene you get. Here you don't. You probably wouldn't expect you would anyway, in the mechanism. There's no opportunity to get another alkene isomer, alkene regioisomer. The Wittig is regioselective. That is, it only gives one alkene in terms of regio constitutional isomers. What else do we get here? That plus what? Reshma? This plus what? Do it?
The E confirmation?
I can't hear.
The E confirmation?
E? As an elephant? I think you're right. Because this is what? Z. Because the high priority group zone is the same side? Uh-huh. Yeah, you also get E. The VIDIG is not typically stereo selective. In some cases it can be, but for us it's not. You get now, this means maybe they're both formed. Does it mean they're both isolated? There's a difference between formed and isolated, right? Show a VIDIG synthesis of the following alkenes. So let's go backwards. How would you make this alkene by a VIDIG reaction? These are the end products, alkenes, VIDIG. What's a VIDIG involved? Reacting what with what?
Ketone.
Aldehyde ketone with a phosphorus ylide. So show an aldehyde ketone and a phosphorus ylide that would react to give compound A. Four plus 2 is 6. But so is 2 plus 3. How about that ketone and that ylide. Then when you take this carbon double bonded to that carbon double bonded, right? Everybody know what an ylide is? Both resonance structures, what's an ylide? Phosphorus, single bonded to carbon, double bonded, triple bonded. We can show it two different ways. There's two resonance structures. But in this the ylide, okay? You gotta know what you're working with. Is there another way to do this? What if we use this carbonyl? And I'll draw an H there because I like to draw H's on my aldehydes. What would we react this with in a VIDIG reaction to give that? This double bonded to what? Phosphorus, right? Two different ways to make the same compound by a VIDIG reaction. Which method is better?
First one you did.
Why is the first one better?
Because when you're preparing the phosphorus ylide, it's
Uh-huh.
better to have a, when you do the SN2 attack, it's better to have a primary.
Uh-huh. And how did you come up with that?
I read last night.
You read something.
Yeah.
Don't read ahead. That's not good. You'll be too prepared. Then you. Very nice. Very nice. Yes, typically it's best to have the VIDIG reagent to be your less substituted carbon. Which is the more substituted carbon in the alkene? That one. That's best to be the Wittig reagent. Why? Because, how do you make this? That would be made from what? Show the synthesis of that Wittig reagent. All the way back from what? All the way back to an alkyl halide. Four carbons. Boom, boom, boom. Boom. React this with what? Any? Triphenylphosphine. That will give boom, boom, boom. 1, 2, 3, 4. With a phosphorus here. 3 phenols. That's plus charge. There's a minus there, Br minus. What do we then react that species with to essentially get this?
Base.
Some type of base. What's your favorite base, Mark?
KOH.
We already used that one. Give me another one.
NaOH.
For an organic chemist, those are both hydroxide. N-butyl lithium? That's a strong base, but it'll work. N-butyl lithium, take an H, electrons behind. What do we get? We get P plus. That's now a minus. There you go. Because these are the same thing, right? These are just resonance structures, right? Yes, this would come from a primary halide. SN2 would be best with a primary halide. To make this Wittig, you would have to start with this, react it with triphenylphosphine, and then base such as N-butyl lithium to get that. Problem is, your triphenylphosphine, you're asking it to do SN2 on a secondary halide. And it might do it, but it also may just do elimination on you. You'd rather have a primary for SN2. How about B? How would you make B? What carbonyl compound and what ylid? We can break the alkene apart into what? Carbonyl compound and Wittig reagent, right? Do you want the carbonyl to be on top or bottom? What if we take that and react it with what? How about that? That'd be it. This carbon, there's 2 H's there. 2 H's there. How would you make that ylid? That would be just one carbon, CH3I. Triphenylphosphine would give P, PH3, CH3 with a positive there and an I minus. Then you treat this with base, remove one H. And now there's only 2 H's there. And I showed the double bond resonance structure. That's the simplest ylid, phosphorus ylid you can have. We could possibly do it the other way, but the other way we would have a secondary halide. Very nice reaction, converting that ketone into this alkene. labeled these because what's another way to make B before we got to Wittig reaction? 2 weeks ago, a month ago, if I asked you to make B, starting from that, how would you have made B? I mean, before Wittig discovered his reaction and published it, gave it to the world, how did people convert that to that? Was it impossible? Was it impossible? Synthesis. Let's go backwards. How do you make alkenes? Well, you can react a carbonyl with a Wittig, but I'm asking you for another way. What's another way to make an alkene? Have you ever made alkenes before in organic chemistry? No. Elimination of what? Water or HBr or of what? Elimination of hydrogen, H2? We've never seen that, although it can be done. We've added hydrogen to alkenes. What do you want to eliminate, Humma? Tell me a compound that we can eliminate something to give that. Hmm? Carbon there. What do you want? What? Samuel, you got some, what can we, give me a compound that we could do something to make that alkene. How about we show that alcohol? If you had that alcohol, could you make that alkene? Can you dehydrate alcohols to make alkene? Aquapyridine? Uh-huh. Or H2SO4, E1 elimination. Is a double bond going to go here or there? What's the final exam?
3 weeks.
Uh-huh. 2 to 3 weeks? Okay. Mark?
Don't you have to use the ender base, so does E2 elimination?
Well, I showed an alcohol. Can you eliminate this by E2?
No, you
How do you make OH better leaving group?
have to.
Protonate it. Can you protonate something under basic conditions?
No.
No. How do you eliminate alcohols? Protonate. E1. E1, is E1 going to give this product, which is called what? Zaitsev or Hoffman?
Often.
It'd be Hoffman coming from this. Can you get the Hoffman coming from that? By an E1? No, E1 always gives Zaitsev. Because E1 always gives the most stable alkene. You cannot, if you treat this with H2SO4, you're going to get that by E1 mechanism. So tell me another starting material to use. Matt?
Can you put the OH on top carbon?
Okay. And how are you going to eliminate it?
H2SO4?
And make primary carbocation?
Yeah, so you have to use alcohol.
Aquapyridine? As long as it went by E2, I think you'd be okay. Yeah. If you did E1, H2SO4 either would not work or it would give that. Because the primary carbocation would quickly rearrange to tertiary, and then you eliminate down here. How are you going to make this? We want to go back to this, right here. Actually, let's start with that. We got to add a carbon. What's the best way to add a carbon to a carbonyl? Somebody said it. Grignard. Yes, here's how you do it. You take this, react it with methyl magnesium bromide, and then H plus workup, and that would give what? I'm not even going to redraw it. What would that give? We added the Grignard and then worked it up with acid. That would give that, wouldn't it? Methyl would add, electrons up, and then the oxygen would pick up an H. There you go. It's going to be more difficult to get. Does everybody see this? Methyl on the carbon, O minus. Methyl on the carbon, O minus. Pick up an H with workup. But if we try to eliminate here, we're going to get that. What do you want to do instead? What can we do? What do you want to convert this to instead? How about instead we're reacting with HBr? What would that give? And give that by what type of mechanism? SN1? Protonate, ionized, tertiary carbocation. Instead of eliminating like this would do, because there's no nucleophile, Br minus would add the carbocation and get that. Your HX is preferred to do substitution. Now we can eliminate this by what mechanism to get that?
E2.
We need an E2. What do you want to use to eliminate this?
Triethylamine.
Triethylamine might work, but in general, what are you telling me? Very sterically hindered base, like potassium T-butoxide or something. E2. That would give, hopefully you get Hoffman elimination. The more sterically hindered your base, the more prone you get to Hoffman elimination. See, you can't do E2 with an alcohol, because you have to have a proton to make that a better leaving group. See, all through here, we had to deal with what? Double bond being here or here. That's not stereochemistry, but what? Regiochemistry. You see, all that is, you have to, regio, is it going to be regio selective? Is the double bond going to go where we want it? See, when Wittig came along, he's like, hey, you want the double bond here? My method, double bond's going to be there. The Wittig is stereo, well, it's not stereoselective, unfortunately, but the Wittig is regioselective. You don't have to worry about where the double bond's going to be. And unfortunately, I see that that's already down there. Right? Okay. So Wittig won Nobel Prize in 1979, shared it with who? A.C. Brown, person who developed silver hydride. A couple of great textbook chemists. I usually tell my A.C. Brown story, but we don't have a lot of time, so I'll move on. I'll tell it anyway. So it was 2001. I was at a chemistry conference in San Diego, and I was on the payphone. You remember payphones? I don't remember payphones. So I was by the bathroom on the payphone, and then A.C. Brown walks out of the bathroom. And he kind of stands right there on the payphone, and I kind of nod at him, and he kind of nods at me. So that's my AC Resident. He stood there a little bit, and about a couple minutes later, after I nodded to him a couple of times, his wife came out of the ladies' bathroom and they walked off. Unfortunately, he died about a year or two later. He died in 2002, 03. Where are we at? There's Wittigs over here. You can see a couple of Wittig reactions along the way to make, I don't know what the Wittig, it says Wittig-Bodin. Apparently Bodin made some type of improvement to the Wittig and got his name on there. I don't know what that is. It's probably a variation of the illid. Instead of the phosphorus with the triphenylphosphines, there's other phosphorus analogs that you could make. It's probably one of those that Bodin came along with. Vioxx. Okay. I think that finishes up the yellow sheet. Last handout. And boy, isn't it a good one. Okay, so aldehyde ketone chemistry we'll continue with. What the first handout was based on mainly was nucleophiles adding to the aldehyde ketone, either by simple addition or the not so simple, where you add and then you do something and you maybe eventually eliminate the oxygen. Is watering, make amines, enamines, variety of things. The Wittig, something added to the carbonyl, the Wittig reagent. We ended up making the four-member ring. It collapses, you get alkenes in a quite unique reaction. With this handout, we're going to move not to the carbonyl, but we're going to move next door. Alpha to the carbonyl, the alpha carbon, alpha, beta, gamma, as you move away from carbonyls. Why? Because the H's on the alpha carbons have some acidity, enough acidity that we can do chemistry with. Just a regular ketone, methyl ketone, pK about 20. Another methyl ketone, about 20. We have to know where H's are. You see, there's no H over here. There's no H over here. Something like this is a ketone. It has H's on both sides. Okay? All four of them have a pK of about 20. At least the first one does. Ketones, about 20. Esters, okay, we will see acid derivatives again, but you can have them here. pK about 25, so they're not as acidic. Nitriles. There's the carbon of the functional group, alpha, pK about 25. These are not as acidic. Why? Well, first off, why is a ketone, why does it have acidity? If we look at this, here, some type of base. What base do you want to use? We'll use, and we'll have to talk about this, we might as well go ahead. Let's use this hydroxide. Take an H, leave those behind. We get CH2 minus plus what? Plus water. Why can we even consider this, doing this? That means this has some stability. What stability does it have?
Resonance.
Resonance. Electrons here, electrons up, and we get resonance structure. It looks like this. Resonance delocalized carbanion. That's why we're able to do this. But pK of 20, how acidic is that? Not very. Carboxylic acid's 5. Phenol's 10, alcohol is 16. Not that acidic. In fact, what side of this equilibrium is favored? Starting materials or products? What's the acid on that side? That with 20. What's the acid over here? Water with 16. Which side's favored, 20 or 16? 20. The weaker acid's favored. And so this equilibrium would look like the other way. We're not going to get much of this. At equilibrium, you'll have a difference of 10 to the 4. What's that, 10,000? At equilibrium, we'll have one of these, 10,000 of these. But that doesn't mean we couldn't use a stronger base. Basically, it's all relative. Which of these resin structures is major?
The second one?
Which one's major?
The one with the O minus?
Yes, major here. Why? Minus on oxygen or carbon?
Oxygen.
Oxygen. They both have same number of bonds, so that's not your answer. Minus on oxygen. That's your major charge there. Sorry, not major charge. Major resonance structure. What does this look like?
Just make sure.
I mean, if I had drawn this protonated, what is that? What's the name of that functional group? I don't know if have we seen this semester? We saw it during the first nomenclature handout of alcohols. Eno. Yeah, what's the donkey say? How's it go? Eno. Eno. Yeah, eno. We saw that in organic 1 when we hydrated alkynes to enols, they tautomerized to the ketone, right? How could you get the enol from that right there? Maybe you treat it with water and it protonates here. We'll get to all that. That's a prelude to what we're going to do in 10 minutes. Why is ester not as acidic? Why is the ester not as acidic? Question is, why is this not as stable? Right? Why is it not as stable? Because the resonance, this would move into carbonyl electrons up. This doesn't move into carbonyl as much. Why not? Because this is donating to carbonyl. Carbonyl's like, oh, we can't have everybody donating to me. I can only handle so much. Since this oxygen is donating, sorry carbanion, you can't donate as much. Esters are not as acidic. Why is the nitrile not as acidic? I mean, we could do resonance here and move this out into nitrogen. But nitrogen is not as electronegative as oxygen. So putting a minus on nitrogen is not as good as putting it on oxygen. So the nitrogen is not as stable. Okay? Everybody can do resonance here, right? Boom, boom. But putting the minus on nitrogen is not as good as putting it on oxygen. Okay, compare. Here, this almost looks like an alpha to carbonyl. That's a carboxylic acid. See, the neighboring atom has an H. We know carboxylic acid is 5. If you also think about it, amides, you pull that H off, that's next to the carbonyl. Why is that more acidic than that? Which is that? Because the minus would be on nitrogen and in resonance oxygen. Here it's on carbon and oxygen. So amides are some acidity. They're more acidic than the ketones. But they're not as acidic as carboxylic acids. Okay, I just erased what we're going to talk about. Enol and enolate tautomers. Enol. The minus form. Here, can I redraw it? Was it right here? Was that it?
Yeah.
When we took off the, this was the resonance structure. And then we showed the enol. Okay, you already had it. What is the anion of an enol called? Enolate. Enolate anion. Okay? The enolate is just the major resonance structure of what we're talking about. It's when you have a charge on oxygen. Now these are in equilibrium. It can be catalyzed by H plus or hydroxide. We already showed the hydroxide right here. Because didn't I take off an H from that and make something and then we did resonance structure? Okay? We've already seen hydroxide do that. That's what we did over here. And I bet some of you are wondering, what did we just do over there? What we did over here was nothing more than we've done for the past two semesters. We just did standard acid-base chemistry and we got to something. So you shouldn't, please don't worry about what we did over here. Just worry about what the name of it is. I think you know how to do it. I suspect that when we name it, that's when, like, what do we do? We just named it. It's just basic chemistry. We took off an H, we did resonance structure. It's called enolate. Oreo. I really shouldn't erase this over here. Let's do it again. We're going to do the same thing over here. What does Oreo mean? Oreo is a way to remember your tautomerization because going from here to here, what's the relationship between these two compounds? They're tautomers. What's a tautomer? Tautomer was introduced in Organic 1. What's a tautomer? They differ by what? What's a tautomer? Dominique? No idea what a tautomer is. Well, these two are tautomers. They were introduced in Organic 1 when we hydrated an alkyne to an enol, and the enol underwent what process to give the ketone? Tautomerization. That's the interconversion between tautomers. Okay? Let's do this. We've already done it with base. Let's do it with acid. Acid catalyzed. Convert from here to the enol tautomer using H+. What do you want to do first in your mechanism? Protonate what? Protonate oxygen. plenty, right? If you're under acidic conditions, what's the first thing you do in a mechanism? Protonate something, right? There we go. Okay, what do you want to do next? And for those who know what Oreo stands for, you should know. Resonance, what are we trying to do? Trying to get closer to that. Show resonance of this. What do you want to do? That oxygen's kind of a greedy little guy there. Let's go ahead and move him up, yeah? Let me resonance. Resonance structure, move them up. And what do you want to do next? What are we trying to get to? One more step. Massimo, what's next? What acid did we use? Let's say we used HCl.
CL1.
Cl minus can take an H, these can move in, you get that, plus what back?
That's
This is an acid catalyzed polymerization to the enol form. Oreo is a great way to remember this. Oreo stands for what? On. We put a proton on. O stands for on. What's next?
resonance.
Then we did resonance. O, RA stands for resonance. Then what do we do over here?
Elimination.
We took an H plus off. Oreo. On resonance off. If you're under basic conditions, which we did over here, what was the first thing we did? We took proton off, and that gave a structure. Then we did what to give this? Resonance. Then what did we do to give this? Put proton on. Okay, at equilibrium, usually your ketone form is highly favored. If you take an IR of this structure, you'll see a carbonyl in the IR. You won't see an OH. Or you may see one that's like so small you can't see it. At equilibrium, it's highly favored. It's like 99.99% this. Usually. There are some compounds where enol form is more favored, such as the 3-dicarbonyl compounds. We'll see some examples on the next page. Which of the following are enol forms of the compound in the box? What's an enol form? Please answer that and show an enol form of this here, the compound there, and explain why. Explain why the enol form is favored in this case. Please also explain why enol forms are favored over here. Okay, you need to do some reading about tautomers, tautomerization, enol forms. It should all be basically a review. It was all covered in Organic 1. Any questions next time? We'll continue from there with alpha substitution reactions. We'll have a quiz on Wednesday, not on this material, but Wittig. We'll end with the Wittig for the quiz. Wittig backwards.
Nah, I'm gonna freaking laugh now. I got a lab report.